Hello. So today we will discuss all the problems of the weekly contest 400, and I was able to solve all the four problems. Um, the rank has not been updated yet, and there were some of the penalties I made. What mistakes I made, I will go through them, and so that you also don't make those mistakes. Okay, so this is a pretty good contest. The It became basically unrated. It would become unrated most probably. So okay, let's start with the first problem. So the first problem says that you are given a string s, simulate events at each second I. If s of I is e, a person enters the waiting room and takes one of the chairs in it. If s of I is l, a person leaves the waiting room, freeing up a chair. Return the minimum number of chairs needed so that a chair is available for every person who enters the waiting room, given that it is initially empty. Okay, so let's start. What does this problem says? Let's start with this example. So we have a string s. Now this string s contains two types of characters. One is e and one is l. E means a person will enter the room. A person, let's say this is the room. So e means a person will enter the room. Uh, Wait a second. Let's make it font family. Let's make it this. Yeah. Hmm. So let's say we assume that let's say we assume that this is a room. So whenever we encounter an e means a person enters the room, and whenever we say that we encounter an L, it means that the person leaves the room. This corresponds to L. So we need to find these are the sequence of events that some person entered here, left here, entered here, a person entered here, a person left here. So we need to find the minimum number of chairs in the waiting room so that every person it is a chair is available for every person who enters the room. Okay, so let's simulate this event. So let's say first we are at E. So let's say E, a person enters. So a chair is allocated to this. Let's say a person is allocated and a chair is allocated here. A chair is allocated. Then the person leaves the room. Okay. So person left the room. So there were no chairs. So let's say we keep a count. Let's say we keep two variables. Current chairs and let's say max chairs. Okay. So currently current chairs is 0, max chairs is 0. A person enters the room, so current chairs become 1, max chairs become 1. So one chair has been occupied by this. Let's say he left the person left. So the chair got discarded. The chair got discarded, due to which the number of chairs became 0, but the maximum number of chairs that were present in the room were 1. Now let's say we came here. Let me erase this. Now let's say the person came here. So again one chair was occupied, so number of current chairs are 1 and it is occupied by E. Then again a second person came, so two chairs were present now, so we'll update it to 2. Let's say a person left, so one chair became empty, uh, so 2 became 1, so now there is one chair currently. Now a person again entered, so again one chair, count of current chair becomes 2, max is 2. Then again a person came, so number of chairs increased by 1, current chairs 3 and max chairs becomes 3. Then the persons kept on lefting, so number of current chairs become 2, then 1 and then 0. So this gone and this gone. So at any particular instance we saw that the maximum number of chairs that were present in a room were 3. Now where could it be? It could be because of, let's say this was cancelled by this, then these two E came, it got cancelled, this cancelled by this. So basically this E and this E made the maximum number of chairs at a particular instance that were 3, and then all of them 3 left. So we need at least 3 chairs, because you could have also thought that there could be 4 chairs. Yes, if there could be 4 chairs, then every person would be accommodated, but one chair would be left. We need to find the minimum number of chairs, so it's basically 3. So just we have to keep on iterating what the problem states, and we take the size of the sequence events. Let the number of current chairs be 0, maximum number of chairs in the room be 0. So if the current element is E, so number of chairs increases by 1 because a person enters the room. If S of I is L, so one player leaves the chair, so number of chairs decreases, and maximum will be the maximum number of chairs at any particular instance. and then we'll return maximum. So this was the solution for problem A. Now let's move to problem B. Let's move to problem B. So what does problem... Let's open other problems also. Now let's say count days without meetings. You are given a positive integer days representing the total number of days an employee is available to work. You are also given a 2D array meetings of size n where meetings of I start to end representing the starting day and ending day of meeting. Return the count of days when the employee is available to work but no meetings are scheduled. Note the meetings may overlap. So let's say we take an example. Let's say we are given a particular number line. Let's say this is the first day because he starts from the first day, is available for work from day one. So it starts from first day. Let's say it's 2, 3, 4, 5, let's say 6, 7, 8, 9, and let's say days is 10. So let's say we have days as 10. Okay, so let's say there are some intervals like 2 to 4. No, let's take 3 to 5, 8 to 9. Let's say we have these two, and we have 4 to 7, 4 to 6. Let's say like this. We have an event like 4 to 6. So we are given the starting and end time. So this is one meeting that started at 3, ended at 5. Next meeting started at 4, ended at 6. And the next meeting started at 8 and ending at 9. So we need to find for how many days was the person not working, was not in a meeting. So person was not in a meeting for this day, this particular day, this particular day, and this particular day. So the answer will be 4. So for 4 days he was not involved in any of the meetings. So now how to proceed with that? Now, whenever we have questions regarding intervals, so we try to sort the intervals. So what we'll try to do here, we'll try to sort the intervals based on the start time. So like if we try to sort the intervals, one interval will become 3, 5, next will become 4, 6, and next will become 8, 9. So we have three intervals which are sorted by their start, which are sorted by their start time. Now, why sorted by start time? We are sorted by start time because if we know that let's say I have this particular event. If I know that for this particular meeting it ended at 6 and the next meeting started at 8, so it is obvious that if there would be more meetings, then they would all be start after 6. They would not start before 6. We basically fixed a particular order that if a meeting ends at 6, so all the meetings after that particular meeting will start, and let's say if for 4, 6 we have a meeting and the next meeting started at 8, so it is guaranteed that all other meetings will start after 8 and 8. Like it could start at 10, it could start at 15. So we have a fixed ordering. So that is why we chose to sort on the basis of start time. So what we see now, first we need to calculate, because the person is available to work from day one. So after sorting, we'll first see the start time for the first meeting. The person started meeting at 3. So basically this particular part, he was not involved. He was not doing any work. So what we'll do, we'll first sort the meetings, and initially our answer will be the start time of the first meeting minus 1, because this was the time he was not doing any work. So we counted that to our answer. Now what we'll do, we'll maintain a global start and a global min. What does global start and global min mean? That global start and global min, like see, first we have the interval 3, 5. We have the interval 3, 5. So let's say global, let's say denoted as G start and G end. So G start is 3 and G end, we know that it's 5. So it's our global start and global end. So this was our first interval. Next we came to 4, 6. So we know that, let's say if in an interval we have this particular interval, we were currently at this interval, and the next interval came, it could have three possibilities. Like the interval could either be this, like we could have three possibilities. An interval, the next interval could either be this because its start is greater than equal to this start. We have sorted it. So either it could come here, or it could overlap, or it could go somewhere here. or it could go here. But this start will always be greater than equal to this start because we have sorted it. So we have multiple cases. So let's say we assume that we encountered or we calculated for this particular interval, and now the next meeting started at this. So we note that this is the gap he was not doing any work. So we'll add this particular thing to our answer. But let's say we assume that the interval, the green interval that we're talking about, let's say that interval goes something like this. So in this case, if they overlap, then we'll consider a new interval starting at this and ending at this. So we'll just take, if two meetings are overlapping, so we'll take the min. So we'll take the min of both the starts, and we'll take the max of both the starts. In this way, we'll cover the all ranges in which meeting was done. But let's say if the meeting was, let's say if the meeting was this, let's say if the next meeting we encountered this and then this meeting came, so the min start will be this, the global start, and the global end will be this. But let's say if the meeting came something like this, so global start will be this and global end will be this. But if the meeting came something like this, so first we'll add this to our answer because he was not doing any work, and then our global max and global min will become this and this, because we are assured that all the meetings after this particular meeting will have start time greater than this particular interval. So that is why. So we'll first take our global start and global min as the first meeting. Now this is our current meeting we are at. Now if we see that this particular interval, this shows that, because what does this shows that we if for a current interval, if for our current interval, let's say this was our global start and this was our global end, and let's say we encountered a current start and current end. So this was our global start and global end, and we are at this particular interval. So if our current start is greater than equal to the end time, so both these don't overlap. So this gap needs to be added to our answer. So we just added this gap to our answer, and we updated our global start and global end to this particular current start and current end. है ना? हाँ, both intervals do not overlap, but in this case both intervals overlap. Now this case could be like here, this case could be like this, and let's say this is en, let's say we have something like this en. So this interval overlapped and this particular interval overlapped. So we'll take the minimum of the starts and we'll take the maximum of the ends. So we'll have a complete interval that will cover all the days in which meeting occurred. And this will not contribute to our answer. Then we know that this will not contribute answer. And in the end, let's say let's say this was the last day, and our last meeting ended at this particular place. Let's say not this, let's say our last day was this and our last meeting occurred on this, our global end came on this. So there are still 2 days left we need to add to our answer. So that is why we have also added days minus end. So in this way we will do the second question. And it is important to note that sorting on the basis of start time actually helped us. Why? Because we know that if we are at a particular interval and the next interval we are dealing, it start, if this is let's say interval 1, so our next interval, that is interval 2, will always come after 1, will always come after this particular start. Either it will come here, or it will come here, or here, or here. So that is why it was useful for us to sort on the basis of start time. So in this way we can do it. Now let's move to the third problem. Lexicographically minimum strings after removing stars. We are given a string S. It may contain any number of star characters. Your task is to remove all the characters. While there is a star, do the following operation. Delete the leftmost star and the smallest non-star character to the left. If there are smallest characters, you can delete any of them. Return the lexicographically smallest string after removing all characters. So let's say we have a string, let's say we have any string like this. Let's say I elaborate the problem. What does the problem says? Let's say we'll copy this AABA star. Let's say AABA star. Okay, AABA star. So what it says is that whenever we encounter a star, we look for all the characters before that star. We look for the smallest character. We have three possible candidates, this, and this. Now we can remove any of these characters, and in the end we'll want to make the lexicographically smallest character. So in this case, we can remove this particular character and we'll get the string as AAB, which is the lexicographically smallest. So we need to find the lexicographically smallest string. So what can we do is that, let's say you have some string. Let's say you have one star, you have another star. Yes. So let's say you have three stars. So we see that, let's say if we encounter at this star, we know that A came here, A came here, and A came here. Now let's say expand the. So let's say A came here. I think I made an example to elaborate that. Okay, so let's say okay, now let's ignore this message. Let's not take this one. uh, hmm. So let's say you encountered, let's say we will have multiple stars. See, we'll have to process the leftmost, because in the string we have to always delete the leftmost star. So we'll always iterate the string from the left, because when we iterate the string from the left, we'll ensure that the leftmost star is always processed first. So let's say this was the first star we processed, and we need to remove, let's say the smallest character was A. All other characters in these places will be greater than A. So let's say we have these three A, and we need to delete any one particular A. So which A should we delete to make it lexicographically smallest string in the end? See, let's say for simplicity, we keep all these characters as B, and C. Let's say we keep these characters as B, C, D, E, F, G, H, I, J, and K. So we can either remove this particular A, this particular A. We can either remove this particular A, this particular A, or this particular A. Now, which A should we remove? See, you'll notice that if you remove this particular A, so the string will become B, C, D, E, F, A, G, H, I, A, J, and K. This is one string. If we remove the second A, our string will become B, C, D, A, E, F, G, H, I, A, J, and K. And if we remove the third A, it will become B, C, D, A, E, F, A, G, H, I, J, and K. So we'll see that all these strings have the same length, because let's say if the string's length is x, so we delete either of A, so all these strings will have length x minus 1. So length can never be useful in comparing, length all will be same. Now we see that all of these prefixes are same. The first character we differed at was E, this. Here E came, here A came, and here A came. So we see that this cannot be a string, this is lexicographically larger. Why did this happen? Because in these two cases, we did not remove the first A. And since A was the smallest, it made these two strings smallest. Then E came, F came, and then A and G. A and G were compared. We see that this A and this G. So this was also not, and this was the lexicographically smallest string. And this string was the result of removing the rightmost A. So we saw one thing, that if before a particular star, let's say there are certain number of A's, let's say, and that length be x. If we remove any of the A's, the length of all the possible strings will become x minus 1. So length is equal for all of them, but it's always beneficial to remove the rightmost a. So because if we remove this particular a, then these two a's will always contribute in making the string smallest. But in spite, if you choose this particular a, so then after a is removed, e will come, and we know that since a is lexicographically smallest, any character apart from the circled will be greater. So this will make the string lexicographically larger if e came in place of a. So it's always beneficial to remove the rightmost a. And it is now simple. Whenever we encounter, if we don't encounter a star, we'll just maintain a priority queue, and priority queue will be of character, comma, index, character, comma, index. So we'll use a custom comparator and sort all the elements with the smallest character first and with the largest index. So 0, 1, let's say this index is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our priority queue will look something like this: 11, comma a, 7, comma a, and 3, comma a, and other elements. So we'll take this particular element. So whenever a star comes, we'll pop this particular element, and we'll pop this particular element, and then we'll keep on moving on. So whenever we don't encounter a star, we'll add that particular character and its index to the priority queue, and whenever a star comes, we'll always pop the first element, because the first element assumes that the character will be the smallest and this will be the rightmost character, because we sorted on the basis of increasing character and on the basis of decreasing index. So we'll always get the rightmost smallest character. So we'll just keep on popping that. So in this particular question, what we did was we maintained the size, and then we had a priority queue. We made a custom comparator which is sorting on the basis of smaller character first and on the basis of larger index first. So whenever we don't encounter a star, we'll simply push the character and the index. But if star came, we'll mark that particular index, the star index, where star came and where the top element came as 1, and then we'll pop it. So what we did here was that whenever, let's say, all these indexes will be marked as false, they were not seen. Whenever we are popping any particular a, whenever we are popping any element, we'll set this to true. We have seen this element. We'll set these two indexes. Whenever a star came, we'll set this star to true and this index to true. It means that they were removed. True means they were removed. So we'll, in the final, we'll just take those particular characters which were not seen, because the seen characters need to be removed. Seen characters need to be removed in the final string. So those which are not seen will push into the answer and we'll return the answer. So this was the problem 3. Now let's move to the last problem. Find the subarray with the closest bitwise AND. Okay. So let's say, what does this problem states that you are given an array nums and an integer k. You need to find a subarray of nums such that the absolute difference between k and bitwise AND of the subarray elements is as small as possible. Return the minimum possible value of the absolute difference. Okay, so I'll explain the problem. What does the problem states? That you are given an array nums, and you are given certain elements. What you need to do is that you need to select a particular subarray. Take the bitwise AND of that particular subarray. Take its difference, absolute difference with k, and we have to try to minimize it. Okay, let's see for this particular example. So we have this. Let's say we have this. So if we write the elements in this order, let's say we have 1. So 1 is basically 0, 0, 1. 2 is basically 0, 1, 0. 4 is basically 1, 0, 0. And 5 is 1, 0, 1. So if we consider the brute force way, we'll first go to I. We'll first start from the ith character and check all the subarrays starting from 1. Like the first subarray would be 1, then it would be 1 2, then it would be 1 2 4, and then it would be 1 4 2 5. Then we'll start from 2, then we'll look for 2 4, and then we'll look for 2 4 5. In this way, we'll iterate over all the subarrays and check the AND on the fly. How? Let's say we are at first. Let's say this array tells that if we start at 1, or we start the subarray at 1, what is the AND? 1. If we start our subarray, consider the subarray 1 2, what will be the AND? It will be 0. If we consider this subarray, what will be the AND? It will be 0. And if we consider this particular subarray, what will be the AND? This will be 0. Okay. Now let's say we start at index 2. When we started index 2, when we started index 2, what is the subarray? What is the sum? What is the bitwise AND? It is 2. When we do 2 and 4 subarray, it becomes 0. And when we consider this particular subarray, it also becomes 0. Okay. Then if we start at this particular subarray, the bitwise AND will be 4. If we consider this subarray, the bitwise AND will be 4. Okay. So now if we start at this particular subarray, so this particular will be 5. So what does this tell? So this array tells that if we start at 1 and consider all the subarrays starting from 1, like this, and this, what is the bitwise AND? In this way, we'll see all the bitwise AND, and we can do it in O of n square. The time complexity will be O of n square, and we can simply do the bitwise AND like 1 minus 3. 1 minus 3 is 2, absolute difference. 3 minus 2 is 1. 3 minus 4 is 1. 5 minus 3 is 2. So the minimum is 1. That is why we took it. Okay. So now we need to see one thing. Like, let's say if we start at this particular index. Now let's say we know a very important property of bitwise AND. We know that for bitwise AND, if we consider the bits, we know that 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. So our bit becomes 1 only for this particular case, and all for the other cases it becomes 0. So you notice one thing, that this particular array is either constant or decreasing. This particular array is constant or decreasing, constant or decreasing, constant or decreasing. Now we should know one property, that bitwise AND is always decreasing in nature, non-increasing in nature. It means that if we start from any particular element and keep on taking the bitwise AND of the first 2 elements, of the next 3 elements, of the next 4 elements, bitwise AND keeps on decreasing. Why? It happens because, let's say, our first character 1 1 0 1. Let's say this is the first element of nums, 1 0 0 1 1 1. This is our, let's say one. Let's say this is 0 1 1 1 0 1. Let's say this is our third element. So bitwise AND will be, so initially for the first, if we consider for this particular element, bitwise AND will be 1 0 1 1 0 1. For the next 2 elements, bitwise AND becomes 1 0 1 1 0 0 1 0 1. And if we take bitwise AND the first 3, it becomes 0 0 0 1 0 and 1. So you see that initially we had 4-bit set, because 4-bit set. Now we had 3-bit set, and now we had 2-bit set. And if we take the value, if we see the value, this value keeps on decreasing. This value keeps on decreasing because this happens because let's say this particular number was there, and if we take this particular number, if both these numbers are not equal, let's say if both these numbers are equal, so bitwise AND will be equal to that number itself. But if both these numbers are not equal, so it's guaranteed that at one bit they would differ. Exactly at least at one bit they would differ. So at one place there would be 1, 0, or it will be 0 or 1. Due to this, the bitwise AND becomes 0. Of particular bit becomes 0 and it also becomes 0. So we see that if two consecutive numbers in the nums array, if there are, let's say, two adjacent elements which are not equal, let's say these two elements, so we see that they differ at, let's say they differed at this bit, they differed at this bit, so they will guarantee differ at one bit, so that bit will become 0. So if initially let's say number had, we know that nums will be 10 ki power 9, so there will be at least 30 bits. Let's say there are 30 bits in the starting. So all the elements, if we keep on taking bitwise AND of, let's say, this particular element, then the next two elements after this, and the next three elements, and next four elements. So if, let's say, in the worst case all the bits are set and the next element is not equal to this particular element, so they will differ at least at one bit. Let's say if they differed at one bit, this bit, so our bitwise AND, initially bitwise AND was this. Now this will become 0, 1. Now this will become 1, 1, 0, 1, 1, 1. So number of bits decreased from 7 to 6. So number of set bits decreases by 1, at least by 1. Let's say the next element could be 0, 0, 0, 1, 1, 1. So next the bitwise AND will become 1, 0, 0, 0, 1, 1, 1. So now this value also got decreased, and now there are only 4 bits set. So the number is keep on decreasing. Here no bit was 0, here 1 bit became 0, here 3 bits became 0. So eventually, if we keep on doing this, at some point of time all the bits will become 0. And after one point, when all the bits become 0, you take any number after that and with 0 and with 0, then you will always get 0 as the result. So we see that for any such, let's say there are multiple nums, we came at this particular nums and we start calculating AND. Let's say AND was A1, let's say AND was A1, let's say AND was something. Now this AND of these two elements will be less than equal to this, of these three will be less than equal to the AND of previous AND of 2, the AND of first 4 elements will be less than equal to AND of first 3 elements, and let's say after going at this particular point, the AND of first these elements became 0. After that all will be 0. So our sequence, so our prefix AND, so if we consider our prefix AND, it will be something like A1, A2, A3, A4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and this will be less than equal to, this will be greater than equal to, and this will be greater than equal to, in this way. So now we need to handle one case. Let's say if in our array we came 9 and then again came 9 and then again came 9. So okay, no, not this. So we see that if our array, let's say if our array contains all distinct numbers, let's say this is, let's say there is 9, there is, let's say there is 171, 85, 12, 3, 1. So for each element I, we'll go to at max 30 steps down. For each I, we'll go to I to I plus 30, because in the next 30 moves, bitwise AND will keep on decreasing and at least one bit will keep on getting unset. So after 30 moves, all bits will become 0. All bits will become 0 and then continue to remain 0. So that is what I have done. So what we'll do for each element, we will just go for 30 elements plus from the current I. From the current I, we'll go to 30 plus elements, because after 31 elements, the bitwise AND is guaranteed to become 0. Bitwise AND is guaranteed to become 0. Bitwise AND is guaranteed to become 0. But there is one problem, there is one problem that I thought initially, that if there are duplicate elements, let's say 9, 9, 9, 3, and 1. So we see that duplicate elements, let's say the bitwise AND here will be 9. The bitwise AND of these two will be 9. The bitwise AND of these three will be 9. Bitwise AND of these three will be something less than 9. And bitwise AND will of course be less than 9. So in this way. So we see that if consecutive adjacent elements are equal, so bitwise AND will remain constant. So we'll just remove multiple occurrences. Let's say if our array is 9, 9, 7, 7, 7, 5, 4, 4. So our array, we'll consider the array 9, 7, 5, and 4, because consecutive elements will never affect our final result. Consecutive elements, because if we consider 2 9s, 3 9s, or 4 9s in any subarray, it is almost equivalent to using 1 9. So the result of AND of 3 9s is equivalent to the result of 1 9. AND of these 3 9 is equal to this. So what I have done is that I have just ensured that, taken a vector v. If the vector is empty, just push the nums of I. But if the last element inserted is equal to nums of I, then don't insert it. So in this way, we have assumed that all the characters adjacent will never be equal. Ensures that adjacent elements are never equal. Adjacent elements are never equal. So this ensures that. And then for each element a of I, we'll just go to 30 steps plus, because after 30 moves, it is maximum. It could be within 30 moves also. Let's say between 15 moves only, all the bits became 0. So we'll keep on doing the AND. We can remove this count, it's not needed. So, and just we'll take the difference. And I have added these two conditions. Like if the AND becomes 0, we know that if the AND becomes 0, after that all the subarrays will have AND 0. So no point of taking that. And what is this condition? This condition states that, let's say this is a number line, this is 0, and this is infinite. Let's say this is our k. And upon calculating the subarrays, let's say we had the prefix and this, then prefix and kept, because you know that prefix and keeps on decreasing. Prefix and become this, prefix and become this. So if prefix and becomes 0, we'll stop. But if our prefix and goes less than k, then we know that all the subarrays after that will have less than equal to k. So the distance will keep on increasing from k. So we'll take the first occurrence when it becomes k in our answer and then stop, because taking all results after that will increase the distance from k, since we need the minimum distance from k. So that is why we'll stop. So the time complexity will be m into O of 30, the time complexity. So in this way, our complexity will become O of n into 30. N into 30 is a time complexity, and in this way, we got a final answer. So the important point here is that the bitwise AND keeps on decreasing, and if let's say the bitwise AND will remain either constant or will keep on decreasing. We always took, in this problem, we only took unique elements. Unique elements ensured that after 30 moves, after each move, at least one bit will become 0, because two numbers are not equal to each other, that is why. So in this way, we solved all the 4 problems. I think, hope you like this video. If there are some queries, I'll be happy to answer them in the comment section. Till then, I'll take off, and yeah, that's it for it. Goodbye. Thank you.